Hello everyone, my name is William Barnes and this is the Physics 2211 Lab 1 presentation. To introduce this lab, it focuses on the observation of an object's change in displacement when moving with a constant velocity on one axis of a coordinate point. The principles addressed in this lab are Newton's first and the position update formula. And to give a quick summary, using the data recorded and simulated, it can be concluded that an object in motion with a constant velocity will stay in motion with a linear increase. However, when testing in real life, other forces such as friction will slow the object to a stop. To give a quick summary on Newton's first law and the position update formula, this law states that an object in motion will stay in motion unless acted on by another force. In this experiment, we do not consider the force of friction. We can use this law to derive the position update formula as shown below, where the current position is added to the velocity multiplied by the change in time. This right here is our experiment. We rolled an object across a tile floor. The system in this situation is the expo marker, and the surroundings are the tile floor that the marker is rolling on, the meter stick used to measure distance, and the constant force acting on the marker to get it to roll at a constant velocity. The initial conditions are the constant velocity at the start of the data points being recorded. We began recording data points at position 10 centimeters, and the constant velocity is set for the computational method, and the position of 0 centimeters at the start of recording data points in the computational method, which we will see soon. The details of this experiment: we rolled an object across the tile floor at a constant velocity, recorded the object's movement, used the meter stick in the video to set scale using the tracker application to collect data points, and then modeled those data points in Google Sheets. So to give you a quick overview of the computational model itself, we set the initial position and velocity vectors based off of the initial velocity that we've recorded itself, set the delta t based off of the data we've recorded as well, and then compute the position update formula using the predetermined time steps within the loop. As you can see right here, the ball's x position is updated based on its current position and the velocity multiplied by the change in time. And then the time and ball position are printed at every time step. So this is the output of the computational model. As you can see, that this is a linear increase, and the time is printed out with the movement in centimeters. The graphical data comparison shows that the simulated data is linear while the recorded data will trail off due to the force of friction. Our data conclusions show that the simulated data points show a linear increase in position as expected, and this is because the net force is 0. Therefore, there's no force that will stop down the object, meaning that according to Newton's first, it will theoretically never stop. The recorded data points also show a slow decrease in position change, which is due to the force of friction. Regarding our what-if situations, if the x-axes were flipped, positive x to negative x, when recording this data, in both the observational and computational model, the graph would simply be flipped over the x-axis. The graph will have the same structure, although it's flipped, and the slope of each line will simply have its sign changed. Next, the closest that our observational model has to net zero force is at the initial velocity, which is why we used a small sample size to set our velocity in the computational model. And the additional forces in play in our observational model are the force of the object being pushed in the positive x direction and the force of friction in the negative x direction. That concludes my Lab 1 report. Thank you for your time.